plus 90. Plus 90. Now, to find our period, let's look at our two waves here. Let's see. From the periods of the two waves will be the same. So we can just grab the period with either one of these waves. Let's say that one. Grab the period. And now grab the time difference of the phase shift, a delta lowercase t. So between these two peaks would be the phase shift, the time phase shift. Okay, great. So now, take the ratio of the delta t over the period, and it should equal 1/4 if it's an ideal inductor. All right. What does that mean if it's an ideal inductor? Well, we have something that could help us make it more ideal, and that's that third toy that was in my present. A piece of soft iron. What the soft iron will do is it will make the inductor more ideal. It will condense the magnetic flux, so more of the field lines are going into the center of the inductor. So let's see here. Let's take another look at this phase shift. All right, so let's look at that phase shift right there. And now I'm going to take the soft iron core. I'm going to put it in the solenoid. Aha! Okay, so now let me move this back down. Look. Yes. Yes. The phase shift is now more pronounced. It's much more clearly a quarter of a wave, the 90 degrees phase shift. Much clearer. The soft iron core has made this a more ideal inductor. All right, terrific. So now we know what to do. Position these. Use the crosshairs in the center. And find the number of boxes times the time per box. That will give you the period of one of the waves. And then find the number of boxes that represents the phase shift, that number of boxes times the period. And then take the ratio, see if it's 1/4. Okay, so now I recommend you play with this some more before you go on to the next part. At the end of the write-up, it'll tell you to start playing with the transformer. I recommend you start doing that play now. So why don't we start playing now? I'm going to turn the voltage, I'm going to put it on the same scale. And the first way we play is, let's look at both of these and start playing with the frequency. All right, so there's these buttons here. We can go up to 1K. Let's take a look at that. Okay, all right. Go up to 10K. Interesting, okay. And you go up to 100K. So also, some of the things you can do is change to square waves. Interesting. You can change to triangle waves. Take a look at those and you can start playing. So let me go back to the sine wave. Now, another thing you should do is sweep the frequencies. And see, there's a knob here. There's a knob here that when you turn, it'll increase the frequencies if you turn counterclockwise. And let's look now. Let's study this. Interesting. Interesting. So hang on. Let me center both of these. We're gonna put it to ground, center it, put it back to AC. Now let's watch that again. So once again, that larger one is the steady source voltage. That's not going to change. And then that's the voltage across the solenoid. And let's now increase the voltage. Let's increase the frequency. Oh. Interesting. Now I'm going past it. And now let's take another time look at that. Okay, so now I'm starting again. I'm increasing. Oh, wow, okay. And then as I keep going, it falls down again. So there seems to be a certain frequency that two things happen. The frequency, the voltage across the solenoid becomes approximately equal to the source voltage, and the phase shift goes away. At this frequency, it's almost like the inductor isn't there anymore. And it's just now the resistor that's the only thing in the circuit. This is called resonance, and it can only happen if there's a capacitance, and there is a capacitance of this, and it will be given to you on the right of somewhere. So, let's see what this means. So this means that we have an RLC circuit, a resistor, an inductor, and a capacitor in a series. So let's just look at the impedance of the inductor. One of the things that I told you in the beginning, because of that negative sign, that the more you try to change the magnetic flux, the more the EMF fights it. So this makes sense to us. So the internal impedance is directly dependent on the frequency. So the higher the frequency, the more the inductor is going to fight. The capacitor is the opposite. The lower the frequency, the higher that impedance. So there has to be a certain frequency where they cancel each other out. In other words, there's a certain frequency where those are essentially not in the circuit anymore, and all you have is just a resistor circuit. That's called resonance, and it happens when they're equal, when those two impedances are equal. So you can do a little algebra, and you have omega is 1 over the square root of LC, and then we'll switch it to a frequency we're more comfortable with by including the 2 pi. The resonance frequency will be 1 over 2 pi times the square root of LC. That's the resonance frequency. So I recommend you calculate it and see if that's what you get. Okay. So now